Invite our first speaker, Dr. Francesco Shankar, to talk to us about the formation and evolution of the most massive galaxies in the universe. So if you would like to welcome him with a round of applause, please. That would be
great. Thank you very much. It is a real pleasure to be here today, this evening. Hello everyone. So, you can all hear me fine, right? Yep. Okay, great. So, I'm Francesco Shankar. So, I'm going to talk about the zoology of galaxies, so how galaxies, what we mean by galaxies in the universe, how they form, so I'll give you a flavor of all of this. But before I start, I think it's right to ask the question, who's this guy talking to us, right? So, I'm a person who's been extremely passionate about science and space since I was a kid, very young kid. So because of that, I started studying physics back in Italy, and then I moved for a PhD in astrophysics. And then after that, I moved on doing postdocs in Ohio, Germany, France, and then I became a staff member here at the University of Southampton. And my role is to, among other things, besides teaching, is to develop theoretical modeling of galaxies, black holes, and dark matter. So this evening, what I'll do is I'll try to guide you through the longest journey of your life. Okay? The longest means in terms of space and time. Now, before we start, could I kindly ask all of you to get a link on this website, on this MeToo website. This will allow us to start having some sort of engagement and discussion between us. So I will ask a couple of questions during the talk, okay? And also, through this website, you will be able to send me feedback and comments, okay? So, if you just did not like the talk, you can say it, okay? It's anonymous. And, but also if you have liked it, or if there are things that I can improve, it's great to have your feedback, okay? So, so let's start. Shall I move? Done?
No.
Not yet? 5, 4, 3. Done? No? Nearly done? Nearly there? Yes? Maybe? Possibly? Okay. So, let's start with the very, very first basic question. Okay? What do you hope to learn from this talk? So, what galaxies are made of, what supermassive black holes are and made of, what dark matter is and made of. All of the above. So for those of you who answered number 3, I can already tell you that I will not be able to answer that question. But 16, 17, 18, 1, 2, 3, 20. I'll give you another 3 seconds. 1, 2, 3. Oh, all of the above. Excellent. Okay. Very good. So I'll try to do that. Okay, so in fact, I will try to give you a flavor of galaxies morphologies, galaxy evolution, galaxy merger, supermassive black holes, and conclusions in 30 minutes. Okay, so this is planet Earth. Planet Earth is within the solar system. Okay, I'm sure all of you have seen this picture once before. Okay, and now the question is, look at this picture over here, right? They all lie on a plane and they orbit around the sun. So now the question is for you, is, why is it that they're not following on the sun, right? They've been doing this for the past 4 billion years, and they will hopefully continue doing so for another few billion years, right? Until the sun becomes a red giant and destroys everything. So, why is it that you think this happened? Dark matter? Maybe? Something else? What happened? One? Two? There is a 20th person who comes in always late. 1, 2, 3. Yes. Very good. And can anyone tell me what that is?
Gravity.
Yes. Very, very close. Slightly more technical?
Momentum.
Yes, angular momentum. Very good, very good. Okay, now let's move on. Let's go beyond the solar system. What do we have? We have the Milky Way. This is an artist's rendition of the Milky Way. Okay? So the sun is approximately here at 8 kiloparsec from the center, and this is the Milky Way. So this is the stellar bulge, and these are the spiral arms made of gas and stars. Okay? Our Milky Way is a spiral galaxy for obvious reasons. It's called a spiral galaxy. Now we could ask ourselves, okay, just to let you know, so this is what you see, this patch over here is 3,000 light years across, okay? So that might not really ring any bell, right? 3,000 light years, okay, fine. What do you actually mean by that? Well, just to give you an idea, a light ray travels around the Earth 7 times in a second approximately, okay? So light is extremely fast. Really, really very fast. Yet, it takes 100,000 years, give or take, to go from one edge of the galaxy to the other. 100,000 years. Okay? It's a long time. But the galaxy is just a tiny dot in the universe. Let's go beyond the galaxy. So this is the Milky Way. Now we go out of the Milky Way. What do we find? Well, we find over here the closest massive galaxy, which is the Andromeda galaxy, another spiral galaxy. And then around the Milky Way and around the Andromeda galaxy, you find a number of dwarf galaxies, small galaxies. They're called dwarf galaxies. Okay? So this is what our local group looks like. And if we go beyond that, we will find other structures of galaxies. These are called the groups and clusters of galaxies. This is an example of a cluster, of a galaxy cluster. What is a galaxy cluster? It's an ensemble of thousands of galaxies, as you can see over here, right? Each dot is a galaxy. And you can also see these arcs over here. Can you see them? These are weird things that are happening over here, and I will guide you through that in a moment, in a few slides. Okay? Now let's step beyond the clusters of galaxies. What do we see? Well, this is an image from the Sloan Digital Sky Survey. Okay? We are here at the center, and this is an image of a scan of the universe at very large scales. See, all these filaments are galaxies and clusters and groups of galaxies. Okay? Each dot over here. You can see this is to compare the area of this large-scale structure. You can compare this tiny dot over here is what Hubble has seen. This is the Hubble Deep Field. Okay? So this is the Hubble Deep Field. It's just a tiny portion of a vast universe. Okay? So the take-home message is that the universe is infinite. Practically speaking, it's infinite. Okay? Okay, so I'm sure I've convinced you that there are zillion of galaxies out there. Okay? I'm sure I've done that. But now let's try and get a sense of what these galaxies actually are and look like. Okay? So this is the Hubble, the so-called Hubble's classification scheme, the pitchfork. And what you see over here is a classification of galaxies divided by morphology. So over here, on the left-hand side, are the most massive galaxies called ellipticals, and at the center over here, they are the lenticular galaxies, and over here on the right-hand side, you have the spiral galaxies, our Milky Way. At this edge of the figure over here, you start having the so-called irregular galaxies. So galaxies, there's a vast zoology of galaxies. Okay, galaxies, there are millions, billions of galaxies, and all of them come in different classes. Okay? So this is a more recent image, classification image of galaxies from the Spitzer telescope, and you can see over here that, of course, the zoology has increased, right? The different types of morphologies from this one, from Hubble to what we have now, but roughly speaking, the trends are the same. So let's start to understand a little bit how astronomers actually classify galaxies. Okay? So let's start from spirals. Okay? These are spirals are called with the capital letter S and followed by a tiny letter A, B, C. So A are the galaxies with the larger bulges at the center, and SC with the tiniest bulges, stellar bulges at the center. And also the winding of the spiral arms is different between SA and SC, as you can see over here. So let's try and play this game. So if you look at these images, how would you classify yourself, these galaxies? Let's start from this one, M81. What would you think this one is? SAB. M63. SBC. Okay, good, well done. NGC 2997.
B.
C.
Okay, there is a trend over here, right? What about this one?
That's a C.
Not the spiral.
Oh, D. Is it?
Yeah, that was a bit of cheating. There is also D. Yeah. So you can see that galaxies go from SAB to SD, and the morphology changes. The spiral arms change, the morphology of the spiral arms, as well as the bulge. What about our Milky Way? This is an artist's impression again, because we cannot really, because we are inside the galaxy, we cannot take an image of the galaxy like this one. But this is what we think the Milky Way is based on the data we have. So how would you classify the Milky Way? B.
BC. BBC.
It was tricky. Now, actually, you can see that there is a capital B over here at the center, in between S and B. This capital B means that there is a bar, okay? And in fact, all galaxies that have a bar also come in the name, they have a capital B inside, okay? So these are the lenticular galaxies. They are classified, so the lenticular galaxies, which are in between ellipticals and spirals, these lenticulars are characterized by not having spiral arms. They have a disk, but not spiral arms, and they have a bulge, which is quite massive, and they're usually classified as SB0. Okay, so let's go to ellipticals. Ellipticals are classified in this way. Capital E followed by a number which goes from 0 to 7. 0 means a circular shape on the sky, 7 means a cigar. Okay? So let's play the game again. NGC 3377. Yeah, very close. NGC 3465. M32. M89. Very close, very close. Good. So you got it, right? So this is how we spend our time. Okay. These are the irregular galaxies, so which are at the other edge of the diagram, and you can see they are irregulars for a specific reason, because they don't really fit in any of the class I showed you before. So they don't have any real clear morphology, and they're called irregulars. Okay, so I showed you that there are zillions of galaxies out there. They come in different classes, okay? So, but now the question is, why? Well, I cannot answer the question. But better to say, how did they form these galaxies, okay? Well, in order to answer that question, we need to get data. And we get data, most of the times, through telescopes, okay? And telescopes, as you know, they are kind of time machines, right? Because when we observe deep in space, because light has a finite speed, okay? It takes some time for light to reach us on Earth. So whenever we observe deep in space, we are actually observing back in time, okay? Is this clear? So this is what we do. So the idea is that if we observe deep enough, we are able to probe different ages of the universe, and therefore we can see galaxies, how they were, the progenitors of these galaxies back in time, by looking with these telescopes deep into space. So this is the idea. What you see over here is the Hubble deep field that I showed you before, and you can see over here very clearly this tiny dot, right? Over here, this red dot, that is possibly one of the oldest galaxies we know of, and it's basically a blob, okay? So this is one of the oldest galaxies, and galaxies were born, started forming very close to the Big Bang, very, very close to the Big Bang. So now if we go a little bit further in time, this is what we start seeing. We start seeing these galaxies that start having these weird shapes. So there are no real patterns like spirals, ellipticals, these nice shapes that I showed you before. When we see back in time, these galaxies appear, very strange. And you can think of these proto-galaxies as assembling, forming their spirals. Eventually, in time, they will settle down, forming the spirals. This is what observations and also simulations, and possibly, I don't know if David maybe will show some of these simulations, possibly, maybe one, about this, we will see how a galaxy is actually formed in these simulations. So, in order to understand how galaxies form, we need to first understand that the most of the universe is made not of galaxies, but actually of dark matter and dark energy. So I showed you that the universe is filled with galaxies, yet the baryonic component, the component made of galaxies, of protons, electrons, which makes the galaxies that I showed you before, is only 4%, that's what astronomers and cosmologists believe, is only 4% of the pie chart of the universe. The rest is something that we don't know. It's made up of dark matter and dark energy. This is the so-called standard model of the universe, suggests, given all the data that we have, that the universe is made up of something else. And because of the existence of this dark matter, we can form the galaxies. So the idea is that these galaxies, each galaxy forms within a dark matter halo. Okay? And what this dark matter halo does is a receiver of baryons. So it collects in time baryons from the background, and these baryons can eventually settle down and form the galaxy. And the galaxy can form just, according to the theory, can form only because of the existence of this dark matter halo. But now you might ask, wait a second, dark matter, you don't even see it, how do you think that this is going to be even important, right? We can't even see that matter. So why do you think that we astronomers believe that there is dark matter? In fact, there is tons of dark matter. How can we even think about this? It's not number 4. No. Why do you think we believe that there is a lot of dark matter out there? And dark matter is the driver for galaxy formation. How much time? Okay, so 1, 2, 3. Sorry for one person. Let's see. other stuff suggests the existence of dark matter. Galaxies sometimes behave as they shouldn't. Well, this is not, this is also true. In fact, if I can tell you, a number of people, a number of astronomers and cosmologists believe that number one is the correct one, right? In fact, many people say, well, you don't see, you can't even detect dark matter, right? And dark matter, I mean, from particle detectors, you can't even see it, yet we haven't seen dark matter directly. So many cosmologists say dark matter does not exist, it's just science fiction, okay? And they propose other theories to compensate for that and explain the data as we know them, okay? So, but the vast majority of astronomers and cosmologists believe that dark matter does exist and dark energy, and because other stuff is suggesting their existence, of course. I'm sure all of you have seen these pictures sometimes, so of general relativity. So, if the universe is made up space-time, okay? If, according to the Einstein general relativity, if the universe is basically built on space-time, okay? And space-time distorts itself with the presence of mass and energy, just like in this picture over here, okay? What Einstein predicted is that light traveling from a background source over here, and because of this obstacle along the line of sight, it will curve its path. And we should see signatures of this curving in images of distant objects, distant galaxies. And in fact, that's what we see. You remember those arcs that I was telling you about before? You remember those arcs that I showed you in clusters of galaxies? Well, those arcs are interpreted in this way. That's called lensing. It's a phenomenon called lensing, in technical terms, by astronomers. And it's just this. So we are the observer, this is the lens, the object, the massive object that distorts the space-time. So the source emits light, but this light is bent because of this distortion. And this distortion is seen, it produces these arcs that we see in the images over here. And we also have the so-called strong lensing. Strong lensing is these arcs that you see around these massive galaxies, these rings of light. These rings of light are not produced by this galaxy, but they are actually produced, and you can prove this by using the redshift, you can prove this, that these rings are not part of the light of this galaxy, but they come from a background source that is being distorted into a ring. So this is a proof in support of general relativity and Einstein's theory, but that's not enough. So we have seen that galaxies exist, that galaxies evolve because we think dark matter exists, and dark matter allows us to form the galaxies at the right pace to see them as we see them today, and also at the right number. But galaxies also are predicted to undergo another phenomenon which is called mergers. So what you see over here are real images of galaxies from the so-called galaxy zoo, of galaxies that are merging, okay, together, they are clashing. And you can see the variety and richness of these merger events. And the idea behind this is that because dark matter, we see in simulation that dark matter merges, we believe that galaxies, because galaxies live in dark matter, if dark matter merges, galaxies that live in dark matter should merge as well. And in fact, we do see this happening. Galaxies merge, and they merge quite frequently and in a different epochs and in different ways. And we also see other things. We also see these concentric shells in deep images of massive galaxies. And again, we believe that these concentric shells and these tidal streams are the result of a number of mergers. And in fact, the theory goes that these massive galaxies, the so-called ellipticals that I showed you before, these ellipticals are mostly, especially the most massive ones, are made through mergers. Mergers are the key driver for forming the most massive galaxies in the universe, but only those ones, not the rest. And this is nicely predicted by the theory of dark matter. And news for you, we are also going to merge. Okay? Not now, but in a few million years. So you can relax and have your drink. So you can see over here, so this what you see on the plane of the sky is what we see as Andromeda. Andromeda is this tiny thing over here, this dot. Okay? This is the most massive galaxy in the nearby universe. But eventually, we know, these are predictions from a numerical simulation, that this Andromeda galaxy will merge with our own Milky Way. And therefore, human beings living on Earth in the future, this is what they will see. On the plane of the sky, they will see an Andromeda galaxy that gets closer and closer, and then eventually, boom, all this mess of stars around. And eventually, what do you see on the plane of the sky? What type of galaxy would you suggest this is? Now that you have the knowledge of galaxy morphology. Is this a spiral? What? Yes, lenticular or even elliptical. So what we learn from these simulations is this: the merger of two spirals, like Andromeda and the Milky Way, may give rise to an elliptical. Okay, so in the last 5 minutes, I want to conclude with supermassive black holes. Now, it has been observed that at the center of all galaxies, including our own, and this is in fact an image, a monitoring of stars at the very center of our own Milky Way, it has been observed that there are supermassive black holes. So, supermassive black holes, in this data, you cannot really see the black hole, right? But what you see is the dynamics of these stars moving around the center. And look at this star in particular. It's moving, when it reaches this point, it moves very, very fast. Whoop. So what we believe, if you play around with the Keplerian formulas that describe the motion, planetary motions, as you know, these type of formulas can give you an estimate of the central mass that is inducing this motion. And this central mass happens to be 10 times 4 million solar masses. So 4 million times the mass of the sun. And this is only a tiny black hole. There are even way more massive black holes. And Noel will describe supermassive black holes in his talk after mine. So supermassive black holes are, we think, the most luminous sources in the universe through quasars. So now you might ask, okay, this guy is really crazy. So how can supermassive black holes be the most luminous beacons in the universe, right? I mean, you're talking about black holes and even supermassive. So how can they be that luminous to become the engines of quasars and therefore become the most luminous sources in the universe? Yes, I'm drinking, that's what it is. Because of lensing, good. Because of other stuff is radiating light, because in fact black holes are not black at all. Well, yes, number 1 and number 2 are both correct in a sense, right? And most probably it's number 2. So number 1 is correct in a sense that we know from Hawking radiation, for example, that black holes are not really that black. But that's a quantum effect that is not what I'm describing over here. It's actually producing tons of light, and it's mainly produced by number 2. It's something else that is producing light. And what is this producing light? So what we believe is happening is that when gas accretes around a supermassive black hole, because of conservation of angular momentum, it starts forming a disk. And this disk of gas around the black hole with a number of processes, it will eventually convert its infall energy into radiation, a lot of radiation, and it will power eventually a quasar, and both Noel and David will discuss this at some level. Now, the interesting thing is that these black holes, this is a zoom in of a radio galaxy, you can see over here, and this is jets, so the black hole will emit jets and radiation and winds, a number of things. So there are a number of processes, a very complex system. And you can see over here, this, from the Hubble Space Telescope, this ring of gas and dust around the black hole. The interesting thing about black holes, at least what I find extremely interesting, is of course their very existence, and also that black holes know about their host galaxies. And what I mean by that is that if you scale up in galaxy, the central black hole will get more massive, as if it somehow knew what type of host was hosting the central black hole. So, and this is very strange because we are talking about very different scales, extremely different scales. We can compare this to a single grape and the size of the Earth. Okay, if the Earth is the whole galaxy and the black hole will be the size of a single grape. If you place the single grape at the center of the Earth, okay, this grape knows about the size of the Earth. Not only that, it will also know, now if you think of the stars in the galaxy as the cars moving around on Earth, that single tiny grape at the center of the Earth will also know how fast these cars are moving on average on the surface of the Earth. So that means it knows how fast the stars are moving in the galaxy, even though they are very, very distant systems. Who knows? Well, there are explanations for this, and it's called AGN feedback, that's something that possibly connects these two scales, and somehow they have talked to each other, and that's the reason why they know about each other. Of course, supermassive, because galaxies, remember, dark matter halos merge, galaxies merge, and if supermassive black holes are at the center of galaxies, well, why not, right? They could also maybe merge eventually. And if two supermassive black holes merge, what do they produce? What do you think they're going to produce?
Gravitational waves.
Yes, excellent, yes. So gravitational waves, as you know now, they've been detected by LIGO. So this is the interferometer by LIGO, and so these are interferometers that work not at the frequencies that we need to detect gravitational waves from supermassive black holes. In fact, LIGO has detected gravitational waves from stellar, possibly stellar size mass black holes, okay, of a few tens solar masses. If we want to detect gravitational waves from supermassive black holes, we need to scale up. And what I mean by that is that this is what we need, LISA. So what is LISA? It's a space interferometer, okay? This is no science fiction, it's actually planned, and these are three space interferometers that will be talking to each other through lasers in this way. And by detecting even tiny delays in the time of arrivals of these lasers, they will be able to tell if there has been a gravitational wave coming in this direction, because each one of them will move in different orthogonal ways, and that will be a signal of a gravitational wave. But in order to reach the sensitivity required to measure gravitational waves from supermassive black holes, we need to wait for LISA. LIGO is not enough. So, take-home message from this talk: galaxies are coming in a variety of forms: spirals, lenticulars, ellipticals. Galaxies live and evolve within dark matter halos, and supermassive black holes live at the center of galaxies. Thank you very much.
Thank you so much, Francesco. That was a great talk. Now, if anybody has questions, please, that would be Great. Come on, guys. I'm sure. Okay, yeah, we have one question.
It relates to the last thing you were talking about, LIGO. LIGO has two four galaxies. Does that mean that it cannot detect a gravitational wave coming in through the centre of it?
What do you mean through the center?
Well, if it's looking for a difference in the time between the two arms, so if the gravitational wave is affecting both arms equally,
No, that's no. So the gravitational wave comes in as a sort of quadrupole. What that means, it will affect the space in two. It will collapse in one direction and stretch in the other direction. Of course, these are very extremely tiny fluctuations, but that's the idea. So it will go in this direction and stretch in the other direction. So this will cause a delay in the path, in the travel time of the two lasers coming in opposite orthogonal directions. So that's the basic idea behind it.
When Andromeda and the Milky Way merge, are there going to be casualties amongst the various components?
Casualty. So the question is about the merging of two galaxies, and what are the, if I interpret it, so what are the consequences of survival for? So the probability for a star-star collision in two galaxies merging together is extremely tiny. And this is because the so-called cross-section, what that means is the area offered by, so in order to hit an obstacle, okay, the larger the obstacle, the higher the probability to hit the obstacle, of course, right? But in cosmological terms, the size of a star with respect to the size of the whole galaxy is extremely tiny. So the probability that a star will go to and collapse and hit directly another star, yes, that's possible, but it's extremely tiny. So most of the reaction is gravitational. So the rearrangement, it will be just a rearrangement of the configuration of the system. So the stars will change their orbits, okay, and the whole energy of the system and mass of the system will change, but that's the idea in merging galaxies. And that's the reason why you saw those tidal streams and all this. Those are gravitational effects that come in.
So sorry, so the conditions on Earth may change as a result of that merger?
Not really, no,
Right.
no, we don't expect that, no, to happen. They will change because of the evolution of the sun. So the sun will change, and of course it will become a red giant, but that is going to affect the Earth, definitely, much more than any other interaction on galaxy scale. Yep.
What kind of timescale are we talking about for a galaxy merger?
Yeah. So that simulation, the point picture that I showed you, those are billions of years. Sorry, those are millions of years. Those are millions of years. Those are millions of years. Yeah. So, no problem.
What determines what type of galaxy is formed? I mean, the elliptical is from the mergers, isn't it? But the different spirals, what determines their formation?
Absolutely, very good question. So my intent was just to give you a flavor, and I told you that those disorganized, inhomogeneous structures at high redshift that I showed you in the deep universe, those will most probably develop into the ordered spirals that we see today. So the idea is that, again, for the conservation of angular momentum, the same effect that controls gravity, the gravity of planets around the sun, controls also this inflow of gas within this dark matter halo. So the gas conserves angular momentum, and it will spiral in, and it will eventually settle down into more or less ordered spirals. And then, of course, there are a number of internal rearrangements that happen, but the idea is that.
We have one more question there, and that will be the last one.
Yes.
I like when you did the metaphor about the grape and the earth. Yeah, to explain. Do you have like a similar one or something you can think about to explain to me about the gravitational waves?
Okay.
Or maybe you can tell me another moment.
Yeah. A metaphor for that.
To put it simple.
Well, I showed you this. Well, yeah, it's very like throwing. The usual one that people do is throwing a stone in a pond, and that creates ripples. And that, so if the pond is in this case, space-time, is creating ripples in space-time. That's the usual metaphor that people use to explain this. So these are waves that oscillate and move at the speed of light, and they propagate through the universe, and then they will hit us eventually. That's the idea. Yeah.
Thank you very much, and let's support Francesco with another round of applause.